Organisms use energy to survive, grow, respond to stimuli, reproduce, and for every type of biological process. The potential energy stored in molecules can be converted into chemical energy, which can ultimately be converted to kinetic energy, enabling an organism to move. Eventually, most of the energy used by organisms is transformed into heat. But the question is, what is the connection of these concepts to the study of thermochemistry? What is the relationship with the so-called enthalpy? How can we calculate enthalpy change using stoichiometry? Well, that is what we are going to discover for this live episode. Hi, I'm Alfie.
I'm Camille.
I'm Christian.
I'm Alea.
I'm Liamel.
I'm Azel.
I'm Kate.
And of course me, the one and only, Neven.
This is
ChemHub,
A kinetic and molecular
Journey that matters.
In our previous discussions, we've learned that energy is the foundation of our universe. It is the property of objects which can be transferred to other objects or converted into different forms, but cannot be created nor destroyed, which is stated in the first law of thermodynamics, or the law of conservation of energy.
A perfect example of this process is No, not that photo. Okay guys, please wait since we are experiencing some minor technical problems. Alright, so a perfect example of this is the process of photosynthesis and cellular metabolism. All living organisms need energy to grow and reproduce, maintain their structures, and respond to the environment. Metabolism is the set of life-sustaining chemical process that enables organisms to transform the chemical energy stored in molecules into energy that can be used for cellular processes.
All these chemical processes are accompanied by energy changes. Each reacting molecule possesses a certain amount of energy due to the nature of chemical bonds. So does each the product of molecule. As the bonds of the reacting molecules break and the new bonds of the products form, energy is released or absorbed, depending on whether the reactants have higher or lower energy than the products.
In thermodynamics, there are two types of reaction classified as exothermic and endothermic. An easy way to differentiate the two reactions are their prefixes, which is endo, which means to draw in, and exo, which means to give off. We will explore more in these concepts after introducing the concept of enthalpy.
Enthalpy signifies as H is a measure of total energy of a system and often expresses and simplifies energy transfer between systems. Since the total enthalpy of a system cannot be measured directly, we most often refer to the change in enthalpy for a particular chemical reaction.
The precise definition of enthalpy is the sum of the internal energy plus the product of pressure and volume. However, for a constant pressure, the change in enthalpy is equal to the heat given off or to the heat absorbed in a given chemical reaction. Change in enthalpy is calculated rather than enthalpy in part because the total enthalpy of a system cannot be measured, since it is impossible to know the zero point. Due to this relation, the change in enthalpy is often referred to as the heat of reaction, and usually has units of kilojoules per mole.
The most basic way to calculate enthalpy change uses the enthalpy of the products and the reactants. For example, the addition of a sodium ion to a chloride ion to form sodium chloride is an example of a reaction you can calculate this way. Ionic sodium has an enthalpy of negative 239.7 kilojoules per mole, and chloride ion has an enthalpy of negative 167.4 kilojoules per mole. Sodium chloride or table salt has an enthalpy of negative 411 kilojoules per mole. Substitute and subtract the quantities, and so the formation of salt releases almost 4 kilojoules of energy per mole.
Now let's discuss the two reactions involved in enthalpy change. Exothermic reactions are processes that release energy, usually in the form of heat or light. In an exothermic reaction, energy is released because the total energy of the products is less than the total energy of the reactants. For this reason, the change in enthalpy for an exothermic reaction will always be negative. Processes that undergo exothermic reaction include freezing, deposition, condensation, and etc.
Another example of exothermic reaction is cellular metabolism, which is found in animals and also found in humans. We consume food to replenish energy, which means that metabolism breaks down biomolecules such as carbohydrates, lipids, proteins, and nucleic acids to provide chemical energy to help us perform our daily activities to sustain life. As a result, the total energy of the product is less than the total energy of the reactants. Therefore, the change in enthalpy is negative and heat is released to the surroundings.
On the other hand, endothermic reactions are processes that require external energy, usually in the form of heat, for the reactions to proceed. Since endothermic reactions draw in heat from their surroundings, they tend to cause their environments to cool down. They are also generally non-spontaneous, and since endothermic reactions yield products that are higher in energy than the reactants. As such, the change in enthalpy for endothermic reactions is always positive. Phase changes that undergo endothermic reactions includes vaporization, melting, sublimation, fusion, and etc.
Another example for an endothermic reaction is a photosynthesis. Plants convert light energy from the sun into chemical energy stored in sugar molecules during the process of photosynthesis. As a result, the total energy of the product is higher than the reactants. Therefore, the change in enthalpy is positive and heat is absorbed from the surroundings by the reaction.
Now, let's move on to the last part of this topic, which is the stoichiometry of enthalpy changes. The energy change associated with the reaction is a stoichiometric quantity and can be treated arithmetically. Now, let's take a closer look for this example. It says that we should find the enthalpy change for the combustion of 35.5 grams of gaseous propane. First step is to convert the mass of propane into moles. So as we solve it, we come up with a molar mass of 44 grams per mole of propane. We will use this in the next step, which is the arithmetic equation. We will first multiply the given mass, which is 35.5 grams of propane, to the molar mass of propane. So in order to cancel both units, 44 grams must be the denominator. Multiply it to the enthalpy change of the chemical equation, which is negative 22.22 times 10 to the third kilojoules over the number of moles of propane in the equation, which is 1 mole. For the final step, multiply all the numerators, which gives us the answer of negative 78,810 kilojoules divided by 44. So the enthalpy change of combusting 35.5 grams of propane is negative 1,791.14 kilojoules. In other words, since it is negative and can be classified as exothermic, the chemical equation therefore releases 1,791.14 kilojoules to its surrounding environment. That ends for today. Thank you for watching this episode of ChemHub. If you were paying attention, today you learned about the basic concept of enthalpy and enthalpy change, including the difference between endothermic and exothermic reactions. Have a great day, young chemists.